In this video we're going to look at related rates of change. Okay, any question we've had so far, we've been given a function and then we've had to differentiate that function to get a rate of change. However, in this one, in these type of questions, we'll be given one rate of change and we'll be asked to find another rate of change. So it won't be just as simple as differentiating the function we get. Alright? If we look at this question, it says e.g. the radius of a circle is increasing at a rate of 2 centimeters per second. So we're given one rate of change. Okay? One rate of change is 2 centimeters per second. Find the rate at which the area is increasing. Right? So in this, we're given one rate of change, the radius, which is 2 centimeters per second. We're asked to find another rate of change, the area. We'll come back to that. Okay, let's concentrate on this for a second. Chain rule states that dy dx equals dy du multiplied by du dx. Well, similarly then, I can say this. Dy dx is dy d anything multiplied by d anything over dx. So as long as I have the same thing here and here, then all of this will equal this. Okay, I can use that to find a rate of change that I haven't been given. So if we look at this, it should be when solving. So when solving problems such as this, follow these steps. Write down the rate of change I require. Okay, so let's say I want dA dt, so it will be the area of something over time, let's say. Right, so write that down. Then write down the rate of change I'm given. So let's say I was given this one. And now use chain rule to link these. So what I mean by that is, I now look for another rate of change that I can get, and I multiply this by that, and I will end up getting the rate of change I want, so long as this question mark and this question mark, whatever goes in there, is the same. Okay? And then I use this information to get my desired rate of change, this dA dt. It'll make a lot more sense when we actually do a question. Okay, so let's go back to this question. The radius of a circle is increasing at a rate of 2 centimeters per second. Find the rate at which the area is increasing when the radius is 3 centimeters per second. Okay, so let's go back to, is it? Okay, so let's look at step 1. Write down the rate of change I require. Well, the rate of change I require is dA dt, okay, which is the rate of change of the area, it stands for area, with respect to time. Okay, so that's what I require. The next one, write down the rate of change I'm given. Well, the rate of change I'm given, let's have a look. The radius of a circle is increasing at a rate of 2 centimeters per second. So I'm given the radius, dr over dt. So basically, the change in radius over time. Next bit then, use chain rule to link these rates. So basically what I mean by that is, I want another rate of change over here that I can get, making sure the two question marks are the same. So if I could get dA dr here, I would be doing pretty well. Why? Well, because I have my A and my T, which I need, because look, the A and the T here, so I have them. And I'd also have two dRs, which is what I need. I need the two of them to be the same. Okay. So that's what I need. Let's see if I can do it. Let's put in what I know first of all. So again, I need dA dt. I have dr dt. It's up here. 2. And then I need to multiply that by dA dr, which is area with respect to radius. Now let's think, is there a formula I already know that will give me the area with respect to the radius? Pi r squared. Area equals pi r squared. Will that give me the area when I put in a radius? Yes, it will. So I need to differentiate that. So if I differentiate pi r squared, okay, and I won't do it out, but I can tell you the answer, is 2 pi r. Okay, let's have a look now. I have dr dt, I have dA dr. In order to find dA dt, I'll multiply both. dA dt then equals 4 pi r. And the last thing I was asked, and here it is, find the rate at which the area is increasing when the radius is 3 centimeters. So if I put in 3 into here, I will get 4 pi 3, which will give me 12 pi. Now think about it. It's the area, the rate at which the area is increasing, well, area centimeters squared, with respect to time. So it's 12 pi centimeters squared per second. Okay, next question. And the more we go through these, hopefully the more you'll understand it. So read the question carefully. The volume, V centimeters cubed, of water in a container is given by the expression V equals 12H squared, when H is the depth of water. So if we put in, whatever, 3 as the depth of water, then it'll spit me out what the volume of water in the container is. The water is flowing into the container at a steady rate of 90 centimeters cubed. So I have a rate of change there. Okay. And that rate of change is with regard volume with respect to time. Okay. Right. So what we're asked then, find the rate in centimeters per second at which the depth of water is increasing. So it's basically how the depth is changing with respect to time. So the depth, rate of change, depth with respect to time. That's what I want. And remember, H stands for depth. Okay, so I want a function that I can put in 3 in for the depth, and it'll spit me out the rate at which the depth is increasing. Okay? Okay, so step 1, let's see what we do. Go back to this. Write down the rate of change we require. Okay, rate of change I require is the depth, which is h, with respect to time. Okay, so the rate of change at which the depth, which is shown by height, changes in respect to time, and it's the rate of change of that, so I have to differentiate it. So that's the first thing we've done. Second thing, write down the rate of change you are given. Well, the rate of change I'm given is this: water flowing into a container at a steady rate of 90 centimeters cubed per second. And what that is dV, the volume with respect to time. Okay, so that's what this is what I want. This is what I've been given. And then last bit. Use chain rule to link these. So basically I need another rate of change over here that has the same thing here and here, and then the same dA or whatever it is on top here, and the same for this on the bottom. Okay. Right, so I need to multiply it by that. So multiplied by, now let's see, we have the dt, okay, so that's that sorted, that dt. What we need then is over here a dh. So dh, and then we have a dv here, so we need a dv here. Right, so what does this say? It says we need a function which will give us the height or the depth in relation to v, which is its volume. So have I any function that will give me the depth in relation to the volume? Let's see. Let's back up here. Well, I have a function that will give me the volume in relation to its depth. Okay, so let's just go down here. I have a function that will give me the volume in relation to the depth. Okay, so notice it's the volume now on top in relation to the depth. And that is V equals 12h squared. Okay, sorry, there shouldn't be a d there. So there I have a function that will give me the volume in relation to its depth. Now I want to get the rate of change of that. So d volume in relation to dh equals 24h. Notice I have dv, so the volume in relation to the height, but I want the height in relation to the volume. Okay, so the other way around. There is a trick I can do. So dh dv, if I flip that and that, if I flip it from top to bottom, okay, just look at this, I can say that's 24h over 1, and therefore I can flip it around to 1 over 24h. Okay, that's just a little trick. Okay, so now I have the rate of change of height in relation to the volume. So that can go in there. Right, so let's put in what we know then. So dh dt, so the rate of change of the depth in relation to the time equals dv dt, I know what that is, 90, multiplied by dh dv. So that is 1 over 24h. Okay, so I have now a formula which is dh dt equals, and we tidy this up, 90 over 24h. So there's my formula that would give me the rate of change of the depth in relation to the time. And to answer my question, I want to find the rate of change when the depth is 3. So put in 3 here. 90 over 24 multiplied by 3. And that will give me 5 over 4 centimeters per second. Okay, last question then. It says a pump is inflating a spherical balloon. The radius of the balloon is increasing at a rate of 1 centimeter per sec when the length of the radius is 2 meters. Okay, so we have the rate of change with regard radius over time. So this is what we have. dr dt. It says find the rate of change of the volume of the balloon. So here's the first question we're doing. Find the rate of change of the volume of the balloon. Okay. So the first thing we do, write down the rate of change we want. And we want dV, volume of the balloon, over time. Rate of change we have, dr dt. What we have to put in there then is dV, that'll take care of this dV, over dr. So we want dV dr, which is the rate of change of volume with respect to radius. Okay, so let's see, we will try to fill in these. So I want this, I have this, hopefully I'll be able to get this. So dr dt, we have that here, the radius with respect to time, it's 1 centimeter per second, so 1 multiplied by, now let's do this over here. I'm looking for a formula that gives the change in volume with respect to radius of a sphere. Okay, because look, it's a sphere here. Okay. So volume of a sphere, well, volume of a sphere equals 4/3 pi r cubed. That will give me the volume with respect to the radius. If I put in something for the radius, it's spitting out the volume. And I want that differentiated. Okay, you would have to use a chain rule here, right? I'm not going to do it for you, but just do it very quickly. 4/3 pi multiplied by 3r squared, which will give me 4 pi r squared. Okay, that's by using chain rule. So 4 pi r squared. So dV dt, so the rate of change of volume with respect to time, equals 1 multiplied by 4 pi r squared, which is 4 pi r squared. Let's answer the question we were asked then. Okay, I know they didn't technically ask it, but it says find the rate of change of the volume of the balloon. Well, we're going to have to presume it's at that time. Okay, so r squared, well, r will be 2 meters. Okay, I'm presuming that find the rate of change of the volume of the balloon is at 2 meters. So 4 pi r squared, and I put in 2 meters here, but I'm going to do it in centimeters. So 4 pi in centimeters. 2 meters is 200 centimeters, and that will give me 160000 pi centimeters cubed per second. That's dV dt. Okay, next question then. If the air continues to be pumped at this rate, find the rate of change of the radius, which is 5 meters in length. So we want the change in radius over time. So we want dr dt. You might think, well, we already have it over here, dr dt. But all we're given is the rate at 2 meters. We don't actually have a formula that we can use to find it at what they're asking us here, which is 5 meters. So we're going to have to do that. Right, so what do we want? dr dt. What do we have? And we have dv dt. And if I multiply that by dr dv, which is the radius with respect to the volume. So the radius with respect to the volume. Okay, so have I a formula that will give me the radius with respect to the volume? Volume equals 4/3 pi r cubed. Right. I want to get dr dv. I can easily get dv dr differentiated with respect to r, and that will give, so if I differentiate this, I differentiate v with respect to r, I will get, as I've done so over here already, there, I will get 4 pi r squared. However, I want dr dv, so I need to flip this around. So put that over 1, and then flip it upside down, and I get 1 over 4 pi r squared. Okay, so let's solve this. So I want dr dt, dv dt, I have it down here, that's what it is, 160,000 pi, multiplied by dr dv, which I have here, which is 1 over 4 pi r squared. I'll get rid of that to give myself a bit of room. Okay, so there is a function that will allow me to find the rate of change of the radius with respect to time. And I was asked to find it at 5 meters in length. So I put 5 in for r. So dr dt equals 160,000 pi multiplied by 1 over 4 pi 5 squared. And if you type that into the calculator, you'll get 0.16 centimeters per second. Okay, last question. At what rate is the surface area of the balloon increasing when r is 5? Okay. So we work down here. Right, what I want then is dA dt, okay, so the surface, that stands for surface area, so the area with respect to time, equals, what I have then is dA well actually no, sorry, what I have is dr dt, which is this. So what I need then is, let me think, let's look at these two. I have the t's, so I need dA over dr. So that's what I need, dA dr. So by any formula, area with respect to radius of a sphere, well, area of a sphere is 4 pi r squared. So if I differentiate that, dA dr, I will get 8 pi r. Okay, so the dt equals dr dt, again I have it up here, so 160,000 pi multiplied by 1 over 4 pi r squared, and multiply all of that by dAdr, which is 8 pi r. And looking back at our question, we want to find it when r is 5. So 160,000 pi multiplied by 1 over 4 pi, and we put in the 5 here, squared, multiplied by 8 pi 5. And if we throw that into the calculator, we will get 640 pi centimeters squared per second. Okay, and this is probably the trickiest part of calculus actually, right? And it requires a bit of practice. So just practice, practice, practice. Okay, thanks guys.